I want to do here is scare you a little bit. The reason I want to scare you a little bit is I want to show you once and for all how, in many cases, what appears to be ominous mathematical notation is simply a rigorous way of saying something which was quite intuitive pictorially to do. The mathematical definition of limit is the following. The limit of f of x as x approaches a equals L means, and get this, given epsilon greater than 0, we can find delta greater than 0, such that when the absolute value of x minus a is less than delta but greater than 0, then the absolute value of f of x minus L is less than epsilon. Now, doesn't that kind of turn you on? See, this is the whole problem. I will now cut you in sort of on the trade secret that makes this thing very, very readable. First of all, to say that you want to get arbitrarily close in value, you want f of x to be arbitrarily close to L, another way of saying that is what? You specify any tolerance limit whatsoever, which we call epsilon. And I can make f of x get to within epsilon of L just by choosing x sufficiently close to a. And by the way, again, in terms of geometry, that's all the absolute value of a difference means. The absolute value of x minus a simply means what? The distance between x and a. All this says is what? I can make f of x fall within epsilon of L by finding a delta such that x is within delta of a. And by the way, this little tidbit over here is simply a fancy way of saying that you're not letting x equal a. You see, the only way the absolute value of a number can be 0 is if the number itself is 0. The only way this could be 0 is if x equals a. So by saying this little tidbit over here, that this is greater than 0, that's our fancy way of saying that we are not going to allow x to equal a. Now, again, whereas this may sound a little bit simpler than the original definition, let's see how much easier the picture makes it. Let's go to a graph of y equals f of x. And in my diagram here, here is a and here is L. And what I'm saying is, I intuitively suspect, let me write down what I suspect. I suspect that the limit of f of x as x approaches a is L in this case. Namely, I suspect that as x gets closer and closer to a, no matter which side you come in on, see? That's why we use absolute value. It makes no difference whether it's positive or negative. As x gets in tighter and tighter on a, I suspect that I can make f of x come arbitrarily equal to L. In other words, if x is close enough to a, f of x, it seems, will be close to L. And by the way, to complete this problem geometrically, pick your epsilon. Let's say that epsilon is this wide. Then since epsilon is positive, this will be called L plus epsilon. This will be called L minus epsilon. Now what we do is we come over to the curve here. All right? Hopefully these will look like horizontal lines to you. When I get down to here, I then project down vertical lines to meet the x-axis. And now all I'm saying, and I think this is fairly intuitively clear, is what? That if x is this close to a, f of x will be within these tolerance limits of L. In other words, for any value of x in here, see, for this neighborhood of a, every input has its output come within epsilon of L. By the way, just one brief note here, something that we'll have to come back to in more detail. In fact, I'll do that in our next example. Notice here how important it was that our curve was not single valued, but one-to-one. In other words, suppose our curve had doubled back, say, something like this. Notice then, when you try to project over to the curve from L plus epsilon, you don't know whether to stop at this point or at this point. You see, in other words, notice that there is another point down here which has the same L plus epsilon value. In other words, whenever our function is not one-to-one, there is going to be a problem when we work analytically of being able to solve algebraic equations and trying to distinguish this point of intersection from this point. You see, if we made a mistake and bypassed this point and came all the way over to here and thought that this was our tolerance limit, we would be in a great deal of difficulty because, you see, for example, for this value of x, its f of x value projects up here, which is outside of the tolerance limits that are given. You see, many things which are self-evident from a picture are not nearly so self-evident analytically, to which we then raise the question, why use analysis at all? Let's just use pictures. And again, the answer is, in this case, we can get away with it, but in more complicated situations where either we can't draw the diagram because it's too complicated, or because we have several variables and we get into a dimension problem, the point is that sometimes we have no recourse other than the analysis. Let me give you an exercise that we'll do in terms of putting the geometry and the analysis side by side.